All right, so the big idea here is this, and only this, is that when you have a right triangle and you draw the one altitude from the hypotenuse, now keep in mind, if we have a right triangle, this leg is one altitude, and this leg is the other altitude. So the only altitude we're talking about here when we say the altitude drawn is the one inside the triangle, okay? The one from the hypotenuse, or to the hypotenuse from the right angle. So the big idea here is that that altitude in a right triangle cuts the triangle into two smaller right triangles that are both similar to the third. So you get three similar right triangles by that segment. Now the reason's straightforward, right? Like the big right triangle has this angle and a right angle. And this little right triangle on the left here has that same orange angle because it's an angle of the triangle, and it has a right angle because the altitude forms a 90-degree angle. And similarly, the triangle on the the triangle on the right is similar to the large because the large triangle has a right angle, and this angle on the right, whatever it is, and the smaller triangle has that same angle and a right angle because the altitude forms a 90-degree angle. So by AA, these two are similar, and by AA, the blue one's similar to the original. And so by the transitive property of similarity, all three triangles are similar to each other. That's the big idea. If you know nothing else, you can solve every problem in this entire section using this alone, okay? The rest of this section is looking at a numerical pattern called the geometric mean and memorized theorems of, well, these segments are the geometric means of these and these and these. And those are memorization. But this is the big idea. If you know nothing else and you can just set up the similar triangles, you can solve everything with ratios and proportions, okay? All right, let's go. So big idea 2 is, what is the geometric mean? Okay, it's the mean. It's the average, right? But arithmetic usually means addition and subtraction. Geometric means multiplication and division. So the normal average, like to get from 2 to 32, you go, oh, look, I add 15 to get to the middle, and then add 15 to get all the way across. Because all the way across, I added 30. So I just cut that right in half, and I said, well, then that means I add 15, then add 15. Okay, the geometric mean is the same thing, but with multiplication. So we go, what did we multiply to get from 2 to 32? Oh, we multiplied by a total of 16. So what would I have multiplied twice to get all the way to 16? So I go, well, that's times 4 times 4, or in other words, the square root of 16. So here you go, all the way across is adding 30. And then you go, what number would I add twice to get there? That's dividing by 2. So it's the exact analogous thing, but like one notch higher on the order of operations. Okay, so I'd multiply by 16 to go all the way across. So if I want to do that in 2 steps, what number times itself is 16? aka the square root. And so we go, oh, we multiply by 4 to get to the middle, and then we do the same multiplication to get to the other side. That's what the geometric mean really is, right? It's the halfway middle, but in terms of multiplication, not in terms of addition. Okay? All right, so exploring the geometric mean. Now, if that's all we knew, okay, so this red M in the middle is the geometric mean of A and B, we can solve for it in terms of A and B. Now, we could do it in 2 different ways. So I'll do on the left in terms of algebra first. Well, if I start with A, and then I multiply by X, and multiply by X again, that just means B is A times X, right? So B is just A times X, or AX squared. Well, now I can just solve for X. I just divide by B, or divide by A on both sides. So I get X squared is A over B. Then I get, and so over here I get X is the square root of B over A. Right, so it's just solving for it, right? If I multiply by X twice to get to B, then I could write B in terms of A, and I could solve for X. Okay, so I got that, right? But we weren't looking for X. We were looking for what the geometric mean, the big red M was. Well, the geometric mean is just the starting value times X once, right? And so we just go, that's A times the square root of B over A, which is what we just got for X. And then we just do some simplification, and that means that M is equal to the square root of A times B, right? And we could even double check that, right? We could say, okay, well, B is just A, and we multiplied by X twice, right? So we plug that in, and we get the square root of a squared x squared, or a times x, which is m. Now, that algebra might have been a little too much for you, and that's okay, right? I love solving things with algebra. It's such a foundational skill that we can always fall back on if we forget memorized theorems, right? But another way to look at this, which is more elegant, is saying, okay, well, if this is the geometric mean, so we're multiplying by x on both of these, well, that means that over here, we could say, well, the ratio of a to m is just 1 to x, because we literally multiplied by x to get it, right? So that's a 1 to x ratio. But also, we multiplied by x to get from the geometric mean to the other endpoint, so that ratio is 1 to x. So these are equal ratios. Equal ratios is just a proportion, so we could say the definition of a geometric mean is simply that the ratio of the starting point to the mean, to that geometric mean, is the geometric mean to the endpoint. Right? Whatever you multiplied to get from a to m, you did the same thing to get from m to b. So those ratios are the same. So that's another way to say the geometric mean. So if x is the geometric mean of a over b, you just go a is to x as x is to b. That's an alternative definition, right? I mean, conceptually, we know that it just means you are multiplying by the same thing twice to get from the start to the end. What was that middle point you landed on, right? That's the idea. But you could absolutely think about it in proportions, and it's such an elegant way to write what a geometric mean is. Okay, so now let's combine the two, okay? So we got this right triangle that we cut with an altitude, okay? We get 3 copies of similar triangles, okay? Well, we could even write out the order there. So the first theorem is just saying, like, which triangles are similar to which. Well, let's look at this, okay? By AA, we know the triangles here are similar. And we could then say, well, then all of their angles match. So I could go ahead and I could add that other angle in here, right? Or you could use third angle theorem. Same thing with the ones on the right here. You could say, oh, well, if those 2 angles match, well, we know the last angle matches too. Okay, third angle theorem, or once they're similar, then all their angles match, okay? But now I could just spin them so that the order matches, right? So this one on the right stays the same. And what I do with the one on the left over here is I just sit it upright. So I spin it 90 degrees this way. Okay, so now it's sitting upright. This one down here, I have to actually spin it, and then I have to flip it over. Okay, so it's actually like you're flipping it kind of through 3D space this way. So this orange one goes on top, and the black right angle goes on bottom. So we spin it around that way. And so with the labeling, we say which triangle is similar to which. Okay, I'm just going to do this freehand for each problem because every problem has different letters. I'm not going to memorize which letter combines with which letter, right? That's crazy town. All right, but we could look at which segments are the geometric means of which. And that's kind of the idea of this geometric mean shortcut. I'm not going to use this shortcut as much, but for the video, I'll kind of bounce between the two. Okay, so just look at those 3 segments. A, B, and C. Okay, so A is the segment from one of the acute angles to where the altitude hits the hypotenuse, and then C is the rest, the other piece, okay? Well, look at this. We split this up into similar triangles, and I just kept those labels where they were. So here's the A, here's the B, here's the B, here's the C, right? But those 2 triangles are similar. So once I spin this 190 degrees, so it's sitting upright, so they're just lined up, it's really easy to see that the ratio is A is to B as B is to C. So it's just similar triangles by AA. No magic here, right? But when you write that, remember that A is to B as B is to C. When you have the A going to B is the same as that same point going to another endpoint, that means that B is the geometric mean of A and C. Okay? So what that means is we go up here, and that means this altitude here is the geometric mean of these 2 segments. So whenever you come across a right triangle with that altitude drawn, you know the altitude is the geometric mean of the 2 portions of the hypotenuse that gets cut into. Okay, so that's one of the theorems. All right, the other one then is saying, well, we have that same thing. Okay, now this time I labeled all these, and now we don't actually need the height of the altitude, so I could erase that H here. We're really just looking at the 2 legs of the big right triangle, and then the 2 portions of the hypotenuse. So let's see what comes out of this, okay? So just labeling this, okay? These are the triangles. I rotate and flip them so they all line up. So here are my triangles. And now look at this. We have B is to A as A is to, so that same geometric mean A. So B is to A, and then start at A and go to B plus C. Okay, well that means A is the geometric mean of B and B plus C because you have the same number here and here. That's useful. Same thing in the other triangle, right? So if we go ahead and erase this, we go, oh, is there a geometric mean? Well, look at this. C is to D as D is to B plus C. Okay, so we got another geometric mean here, D, where this C going to D is the same thing as starting at D and going somewhere else. And so if we look back at the picture, what does that mean, okay? So that means that A is the geometric mean of B and B plus C. So up in the picture, we have A, is the geometric mean of B and B plus C. And then if we look at the other one and we say, okay, D is the geometric mean of C and B plus C. D is the geometric mean of C and B plus C. So in other words, the leg of the big triangle, right? So if we go to the big triangle, this leg up here, this is the geometric mean of this portion from here to here and the entire hypotenuse B. So it's the geometric mean of its portion of the hypotenuse to the entire hypotenuse. That's another theorem, okay? Now again, I don't use these theorems memorized. All I do is remember the one big idea from this section, that is I get 3 similar triangles. And I use those 3 similar triangles with ratios and proportions. That way I have less to memorize, and I have a better conceptual understanding of the subject matter, and I can apply it whenever I encounter this. I don't need to go, wait a second, there was a theorem about which segments. I mean, there's so many little segments. I mean, it's like, is it this one, or 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 even the whole thing? I'm like, God, I don't know what the combinations are. That's crazy town. So I'm going to do it using similar triangles. All right, so let's go ahead and do it. So first here, it's going to ask us to practice some geometric mean. Okay, find 2 numbers whose geometric mean is 12. Well, that's easy. We multiply by some number to get to 12, and then we multiply that by number again. So let's say we multiply by 2 and 2. That means it's the geometric mean of 6 and 24. Or let's say 3, right? We multiplied by 3 to get to 12, and we multiply by 3 again. So that means 12 is the geometric mean of 4 and 36. Or let's say any number, right? We multiplied by 4 to get to 12, so we started at 3, and that means 12 is the geometric mean of 3 and 48, right? So there's so many ways you could go about this problem, but the big idea is whatever you multiply to get to 12, you just do that same number again, and you could have done any decimal fraction, anything there. Okay, so RST is a right isosceles triangle. Well, right isosceles triangle, the only way you can have a right isosceles triangle is if the 2 legs are congruent. You can never have the hypotenuse, you can never have the hypotenuse of a right triangle equal to the other. One was the shortest distance from a point to a line is a straight line, and actually the proof is literally that then this has to be longer than this one, and the reasoning is that in a triangle, the biggest angle is across from biggest side, and you can't have another 90-degree angle in a triangle. So no matter what this angle is over here, it's less than 90, so this side is less. So there's so many different ways to look at it, but the hypotenuse is always the longest side. So the only way to have an isosceles right triangle is if the 2 legs are congruent. Okay, so over here we have a 14, and we have a 9.9. That means that we have 2 congruent legs and the longest hypotenuse, so that means this is the hypotenuse. That means this is the other leg, which is 9.9. That means this is the right angle. Okay. Holly and Ian are finding the measure of altitude SU. Okay. Well, we could do 2 things here. We could either use the theorem. So we go up to our theorem and we say, oh, I skipped the summary here. I want to right pi it. So let's just summarize the whole lesson right now, okay? So to summarize, the altitude of a right triangle cuts it into 3 similar triangles. Got it. Geometric mean, you multiply by the same thing to get to a middle as you multiply to get to the other end, or it's the common ratio. So A is to M as M is to B. Boom. And our 2 theorems are the altitude is the geometric mean of these 2 portions, or The leg is the geometric mean of piece to whole. Okay, so A is the geometric mean of B and B plus C. All right, that's the idea. Geometric mean of the pieces, or leg is the geometric mean of piece to whole. Those are our theorems. So let's go back down here. So if we wanted to use the theorem and not draw out the right triangles, we know that x is the geometric mean of 7 and 7. So that means 7 is to x as x is to 7. All right, got it? So let's go over here and we'll see, okay, so who's got this? So RS is to SU as SU is to RT. So what they have here is segment is to, or leg is to height as height is to leg. That is not true. No, that is just the wrong memorized theorem. And that's why I don't like these memorized theorems. Like, where did they get that? They memorized something and they just wrote it wrong. Not very good, okay? Over here we have RU. So that's the piece is to the height as the height is to the other piece. So that was just the right memorized thing. Okay, but we could explore this in so many different ways. Now, one way we could do this is we could go, well, if this is an isosceles right triangle, so these sides are the same, that means these angles at the bottom are the same. And if the angles are the same and we know there's 90 up here, we can always solve in that isosceles triangle and go, okay, 180 minus 90, what are the leftover angles? Okay, so this is 45 degrees. This is 45 degrees. So the only thing it could be. And it said that you drew the altitude SU. So you know these are right angles. So we just go, oh, let's subtract on the left. Oh my gosh, this is 45 degrees. Subtract on the right. Oh my gosh, this is 45 degrees. Another way to know is when you have an isosceles triangle and you draw any of those special segments, like the median, the altitude, the perpendicular bisector, they're all the same. So you actually knew that this altitude here was also the perpendicular bisector, which, I mean, it's literally shown, and it's the angle bisector, so it split the 90 into 45s. So what that means is this triangle is also isosceles because it was similar to the bigger triangle, which was isosceles, or we just proved 45 and 45, so these are the same, it's 7. And those are the same because on the right it's isosceles. So there's lots of ways we could explore this, and this is actually going to be one of our special right triangles that we talk about in the coming sections. Okay, but yeah, this poor person on the left just used the wrong memorized thing here. It's the geometric mean of x and y, or b and c, or w and q, who knows? So that's why we're going to break it into similar triangles. Let's do one more with the geometric mean. Okay, so there's a couple ways to do this. You could say, shoot, how did I get from 9 to some middle, and then from some middle to 4? And you could algebra this out, right? Or you could say proportion. So let's solve this one with proportion. So we say 9 is to m as m is to 4. Okay, so let's cross multiply. That's m squared equals 36. So that's m equals, technically it's plus or minus. Usually we only talk about the positive version. It would work out because if you multiply by a negative and then multiply by a negative, you still end up getting the positive 4 at the end. But we usually only look at the positive copy. So we go, oh, it's 6. So let's see if that's right. What did I multiply 9 by to get to 6? Well, I had to cancel out the 9, so I put a 9 on bottom, and I wanted to end at a 6, so I multiplied by 6/9, or that's the same as 2/3. So if I multiply 9 by 2/3, I get 6, and then if we multiply by 2/3 again, let's see, 6 times 2/3, that'd be cancel, we get a 2 and a 1, and sure enough, that'd be 4. So the geometric mean of 9 and 4 was 6. Okay, well, let's do it using this algebra up at the top. When we solved for it algebraically, we got that the geometric mean was just the square root of the two numbers multiplied together. So that's one way to do this. We could just go, oh, well, the geometric mean is just the square root of 36 times 49, and there's no addition here, so that's the same thing as square root of 36 times square root of 49, or in other words, that's the same thing as 6 times 7, or 42. So the geometric mean here was 42. And we could just go ahead and check. We go 36, multiplied by something is 42, multiplied by something is 49. And we go, well, I needed to cancel out the 36, so I did that, and then I want to end at 42, so that's exactly what I multiply by. And then we just reduce it, and we go, well, you can divide both sides by 6, so we multiply by 7 6. So let's see, 36 over 1 times 7 6, cancel, we get a 6 and a 1, and we end up at 42. If we multiply 42 by 7 6, then we go, okay, well, cancel, we get a 7 and a 1, and sure enough, we end at 49. So that's another way to do it. Or you could just literally algebra it, and you go, shoot, 6 times x gives us the middle, and then we multiply by x again, and we get 8, and we go, okay, so that means 8, whoa, that was crazy town. We go 8 is equal to 6 times x times x. So what was x then? We go, okay, well, we divide by 6. So that's 8 over 6 equals x squared. So that x that we multiplied by was the square root of, 8 over 6. And we go, okay, so what's the middle then? Oh, well, we started with the 6, and we multiplied by this root 8 over 6. So that would be the geometric mean. And then we could simplify this. We could be like, oh, well, that's 6 root 8 over root 6. We multiply by root 6 on top and bottom. That becomes 6 root 48 over 6. These cancel. We get the square root of 48. And we go, oh, we could simplify that. That's a square root of 16 times square root of 3, or 4 root 3, okay? So that was just a different way to do it. I'm showing you 3 different ways. Now the last one, I'll use geometric proportions, or proportions to find the geometric mean. So we go, okay, so we have 2 root 2 is to m, as m is to 3 root 2. So cross multiplying, we get m squared equals, and 2 root 2 times 3 root 2. I'm just going to rearrange the order there. So that's 2 times 3 times root 2 times root 2, or 6 times root 4, or 6 times 2, or 12. So we get m squared is 12. So the geometric mean is the square root of 12, which we can simplify to be the square root of 4 times the square root of 3, or 2 root 3. Okay, chévere, you guys. Okay, let's go down here. All right, so we could use the memorized theorem, and we could go, oh, look, we have a right triangle, we have an altitude drawn to the hypotenuse, and so we want to find the height of this altitude. Well, we know it's the geometric mean of the 2 segments. So 2 is to h, as h is to 6, and then we just go, well, that means h squared equals 12. Oh my gosh, we just did that number. The height is root 12, or root 4 root 3, which is, the height is 2 root 3. Okay, but in the right triangle, I'm going to actually just solve out and say, shoot, I just came across this problem. I don't know. Well, I could subtract, and I could get this as 4. And then I get these similar triangles, okay? So here's a 1 angle and a 2 angle, and I could just go, okay, well, this triangle here with a 4 and no other side lengths is similar to the whole thing, which is the 1, the right angle, and the 2, and all we have is this, the 16. And that's similar to this triangle on the right that has the 2 angle here, and we have the 12. Now I could go ahead and put in the other angle markers, and I could go, well, they're all similar, so this one's the double marker, and this one's the single marker. Then I could even rotate them, but up here it says find and measure the altitude. So I'm going to go ahead and put an X here. So that means there's an X here and an X here. Now I'm just going to spin and rotate each triangle. So what I've got, if I draw them all lined up, is in this triangle, between the 1 and the right angle is a 4. Between the 2 and the right angle is an X. And that's similar to, between the 1 and the right angle is nothing. Between the right angle and the 2 is nothing. And the hypotenuse is 16. It's similar to this one on the right, I don't need to move at all, is X and 12. Whoa, that angle marker came out crazy. And so these are the triangles that are proportional, just lined up. Well, now I can clearly see that the ratio is right here and right here. So it's just 4 is to X as X is to 12. So that's X squared equals 48. So X is root 48. Or in other words, root 16 times root 3. Or X equals 4 root 3. Very cool. Okay, so find X and Y. So now we're looking at more than just one, right? So in this one, I'll use the shortcut, and in the next one, I won't. So in this one, we know big right triangle, altitude. that means this height is the geometric mean of the two segments. So we know that 8 is to x as x is to 3. It's the geometric mean of the two. So x squared equals 24. So x is root 24. And we'll use that later, but we could also simplify it to be root 4 root 6 or 2 root 6. Okay, so x is 2 root 6 in the most simplified form. And so up here, if we have x and we have 3, well, we have a right triangle with an x and a 3, but we know the x is, and I'm going to use the root 24 version because it's going to be easier for me. Then we could just solve for y using the Pythagorean theorem. So we could just go 3 squared plus root 24 squared equals c squared. So this is 9 plus 24 is c squared. Because the square root squared cancels out, we just get the 24. So that's going to be 33 equals c squared. So we get c equals square root of 33. So that's one way to do that. Or we could have used the theorem and said, okay, we did say we were going to use the theorems on this one. Well, this leg is the geometric mean of the piece here and the piece here. Nope, sorry. Of the 3 and the entire is what I meant. So see, the memorization's hard. So that leg is the geometric mean between the piece and the entire hypotenuse. So let's do that. So between 3 and 11, because we add the 8 and the 3 together, so we go 3 is to y as y is to 11. Right, that's the idea there. And so we get y squared equals 33. Or in other words, y equals root 33. And there's no simplifying there. And I'm sure of that because this is 3 times 11, which are both prime. They don't have a partner value, so there's no simplification that we can do there. So we found x and y. All right, so here it wants us to find x and y. So I'm not going to use the theorem here. Instead, I'm just going to solve it out. I'm going to say, oh, okay, well, I know that this triangle here is similar. So that's x, y, and 2 root 3. I know that's similar to the original triangle. They're rotated different ways. That's okay. That's similar to this, the y and an x plus 2. And we don't have anything for the other side. And then in this right triangle, we have this one here. And I'm going to put double angle marker here. So it's similar to the original triangles. And that's 2 root 3 and 2. So I could go ahead and solve the right triangle and just go, well, I could just use Pythagorean theorem. But first I'm going to rotate these. So I could fill in that third angle here and that third angle here. Okay, so rotating it, I get this triangle is x, 2 root 3, and y is similar to, and I have to flip this one over. So between the 1 and the right angle is a y, and the hypotenuse, oh shoot, I wrote the wrong angle marker there, my bad. The hypotenuse is x plus 2, and we don't have any marker for the other side. And then the last one, we didn't have to rotate at all. Okay, we just got 2 and a 2 root 3. So these are my triangles that are similar. So right away I go, oh, well, I could solve for x using this. But instead, I'm going to just solve for the length of the hypotenuse over here really quickly. And go, well, this is 2 squared plus 2 root 3 squared equals c squared. So that's 4 plus, and now I'm going to write this all the way out, but you could absolutely do the distributing the exponent because there's no addition in there. So that's 4 plus 2 times root 3 times root 3, just by reordering that. So that's 4 plus 4 times 3, because square root of 3 times square root of 3 is square root of 9, or 3. And then that's 4 plus 12, or 16 is c squared. So c is square root 16, or 4. Okay, so this was 4 right there. That's good to know, okay. Well, these are all similar. So now we can just set up any ratios we want. Let's do this one right here to solve for y. So I'm going to say 2 root 3 is to y as 2 is to 4. Cross multiplying, I get 2y equals, this is 4 times 2 root 3, or in other words, 8 root 3. Equals 2y. We divide both sides by 2, and we get y equals 4 root 3. All right, on the left over here, solving for x, we'll just use any other proportion here. And so I'm going to do that original proportion like this. And I'm going to say x is to 2 root 3 as 2 root 3 is to 2. So cross multiplying, 2x equals that same 2 root 3 times 2 root 3 that we just did, but let's pretend we don't know what it equals. So 2 times 2 times root 3 times root 3, so that's 4 times root 9, that's 4 times 3, that's 12 equals 2x, so that means x equals 6. Okay, so we have a 6 and a 4 root 3 here for our sides, and if we wanted then, we could go ahead and solve for all the values in this triangle, but it didn't ask us to, it just asked us to solve for x and y. Okay, now here's a real world application that you might come across. This is just using a right angle to measure the height of something you don't know. So it's saying this person's making a banner for the dance committee, and it has to be as high as the wall of the gymnasium. Whoa, that is a tall banner. Okay, so she held a book up to her eyes so that there was a right angle and lined up her eyesight all the way up to the top corner and bottom corner. And it says if she is standing 12 feet from the wall. So what that means is the distance, right angle altitude, well, I should connect to these first. So right angle altitude there, that distance is 12. Okay, so I'm just going to draw that in here. This is 12. And then it says if her eye level is 5 feet, so that means from her eye down is 5 feet perpendicular. But another way to write that is put that right here in the triangle. How high is the wall? So we really need to find this other segment, and then we just add it 5 plus that. Okay, so what we've got here is a right triangle with the altitude drawn. The altitude's 12. This piece of the segment is 5, and we're looking for x. So let's use the theorem this time. So this is the geometric mean of the two segments of the hypotenuse. So we go 5 is to 12 as 12 is to x, because 12 is the geometric mean. So cross multiplying, we get 5x equals 144. I don't know why I wrote it so high there. And then we get x equals 144 fifths. And yeah, I mean, it doesn't work out nicely, but we could do it. So that's equal to 28.8, I think. And so if that's 28.8, so that means this height up here was 28.8. What that means is the total height of the wall is 28.8 plus 5, or 33.8. And then whatever units. It was all in feet. Okay? Find the measure of the altitude drawn. So again, I'm going to use the theorem once and go, oh, the altitude is the geometric mean of those. So let's put an x here. So 5 is to x as x is to 9. Cross multiplying, x squared is 45. So x is root 45, which is root 9 root 5, or 3 root 5. Okay. And then on the right here, I'm not going to use it this time. I'll say no. Although I can tell that this is the geometric mean of those two. So it's going to be, what's the average of two numbers that are the same? Whether you're adding or multiplying, it's the same number. So I can tell already this is going to be 12. Another way to tell is this is an altitude that is also a bisector. So it's also a median. So it's also a perpendicular bisector. So it's also an angle bisector. So this is angle bisector, that means this is 45, 45. That means this was 45, right? So like we know this is all isosceles, and we'll get to that special right triangle later. But for now, let's say, oh, well, that's interesting. Oh, wow. Okay, we want to solve for this. Well, I know that this breaks it up into two similar triangles. So let's put an angle marker here and an angle marker here. And we go, okay, well, this triangle is similar, so 12 and x, is similar to the original triangle, and that's 24, and we have nothing else. And that's similar to the bottom triangle, like this, and that's a 12 and an x. Now I could finish the last markers here. I could say, well, that means this is the double marker and this is the 1, just by third angle theorem or similarity. So I'm going to put them upright this way this time. So we have the 1 angle, the 2, and the right angle. So this is a 12 and an x. And that's similar to, we're not going to end up using this one. So it's similar to the one on the right. I'm going to draw it shaped the same way, or oriented the same way. And between the 1 marker and the right angle is x. And between the right angle and the 2 was 12. And so our ratio here is x is to 12 as 12 is to x. Cross multiplying, we get x squared is 144. and we get x is square root of 144 or 12. Okay, very cool. Now we're looking for x, y, and z. So we're looking at a lot of problems, this way, forwards, backwards. So again, I'll use the theorem once, and then I won't use it the other time. So in the first one, z is the geometric average of the two segments. Okay, so 3 is to z as z is to 8. So z squared equals 24. So z equals square root of 24, which is square root of 4, square root of 6. So z is 2 root 6. Okay, now the theorem that is much less commonly used, right, is this leg is the geometric average of piece to whole. So that means y is the geometric average of 3 and 11. So we go 3 is to y as y is to 11. So y squared equals root, no root yet, equals 3 times 11, 33. So y equals root 33. And that's as simple as it gets. And then lastly, same thing, but on the other side. So x, the leg of the big triangle, is the geometric mean of the piece to the whole. So we get 8 is to x as x is to 11. So x squared equals 88. X equals root 88. This one does have a way to simplify. There's a 4 in there. So that's root 4 times root 22. So x is 2 root 22. That's cool. Okay, now for the other one, we're not going to do it. Let's just do similar triangles here. Okay, so I'm going to put one angle marker 2. So we get this triangle that looks like this. And I'll put in whatever things we have. This is 6, and I'll label this as x minus 6. So we have 6, y, and 8. That's similar to the big original triangle. And this is an x, a z, and a y. And that's similar to this triangle here, which has a right angle and a double angle. And that's an x minus 6, an 8, and a z. And then I can finish off the angle markers. This one on the left has the double here, and this one has the 1 here because they're all similar. All right, so I'm going to rearrange them to be the 1, 2, just like the way I like it there, okay? Oh, and look, we don't have to rearrange the big one. That's nice. And then we'll rearrange this one over here. Okay, so these 3 triangles are similar, and they're all rotated the right way. So between the 1 and the right angle is 6. Between the right angle and the 2 is the 8. And this is y. Well, Pythagorean theorem there, I could just get y equals 10 really quick. That's just a 3, 4, 5 triangle times 2. You just go 6 squared plus 8 squared equals c squared. 36 plus 64 is c squared. 100 is c squared. C is 10. That was a quick way to get y. Or we could use proportions. Okay, so now we have a 10, a z, and an x. And then spinning this last one between the 1 and the right angle is an 8. The hypotenuse is a z. And between the right angle and the 2 is the x minus 6. So now we got to solve for the x here, okay? Well, I think the easiest is this right here, since we already have numbers. So that'd be 6 is to 10 as 10 is to x. So that's 6x equals 100. So x equals 106. We could divide both of those by 2 and we get 50 thirds. Okay, so x is 50 thirds. All right, another way you could do this is you could simply say, well, these triangles are similar, and I went from a 6 to a 10, so what did I multiply by? Well, I divided by 6 to get rid of the 6, and I multiplied by 10 to make it a 10, right? That's exactly what I multiply 6 by if I want to get 10. And so that's really, I multiplied by 5 thirds. So you could say this side was the starting 10 times 5 thirds, and this was the starting 8 times 5 thirds to get all these sides. So z would be 40 thirds, and this would be 50 thirds. So that was just a shortcut way to get y. Is he just showing you, once you know similar triangles and proportions, you can get everything. But let's pretend we didn't have that. We go, oh, no. We don't have this crazy cool scale factor logic that we can use. But we did just solve for x. We go, okay, so this is 50 thirds. If we wanted to write it down here, this is 50 thirds minus 6, whatever that comes out to be. Okay, but we want to solve for z here. What could we do with z? Well, we could say z is to 8 as, and then again, the 6 is to 10. So we could go, all right, so 6 is to 10 as 8 is to z. So cross multiplying, we get 6z equals 80. So we get z equals 86 or 40/3, which was exactly what we got when we multiplied 8 by 5/3 anyways. So it all worked out. Okay, so that was z. Perfect. All right, so what's the geometric? What about if you're given the geometric mean and one of the extremes? This is so easy peasy, right? You literally go, well, I start with 7, I multiply by something to get root 17. Then, if I multiply by something, so I mean, literally, what do you multiply by? You divide by 7 to get rid of 7, and you multiply by root 17. So this is exactly the thing you multiply by to get that. So if we just multiply by root 17 over 7, then we get, well, just off to the side, we go, let's see, root 17 times root 17 over 7. So that's equal to 17 on top over 7. Oh, that was nice. Okay, 17/7. That was the other one. For the second one, let's actually use the geometric mean concept of proportions, okay? So that was 33. I just kind of did it based on the very definition of geometric mean. So 34, 12 is the geometric mean between x and y. So that means x is to root 12 as root 12 is to y. That's the idea of geometric mean as a proportion. And that tells us that y is root 3. So let's go ahead and erase y here and put a root 3. Okay, so let's cross multiply. So we get x times root 3 equals root 12 times root 12. Well, any square root times itself is exactly like half of the heart necklace with half of the heart necklace. Like they complete each other, right? They exactly are saying what number times itself is equal to 12. And wait a second, I found that number, so that's equal to 12. Or you could say this is a square root of 144. Either way, I like thinking about it as beautiful completion. All right, so now we just need to divide by whatever number is being multiplied by x. So we get the answer is 12 divided by root 3. We never leave a square root on the bottom, so we rationalize that denominator just by multiplying by that square root on top and bottom. So on bottom, common mistake is people just get rid of this. That's not what happens. Square root of 3 times itself, again, is completing itself. I strongly recommend you look up the poem about the square root of 3 and the loneliest number. It was in one of the Harold and Kumar movies, but it's a great poem with all these math puns about square root of 3 being completed. Anyways, it's a very romantic wedding poem. Square root of 3 times square root of 3 is 3. And on top is 12 root 3. But look at that. I can reduce the 12 over 3 to be 4 over 1. So really this is 4 root 3 over 1, or just x equals 4 root 3. Okay, so then sometimes, always, or never. And I think this is the end. Oh, no, we did the challenge problem. Okay, the geometric mean for consecutive positive integers is the average of the two numbers. Well, we could just try it, right? So let's try like 1 and 2. Well, the average of those two numbers in terms of arithmetic mean is 1.5. So you add the same thing. Well, let's see if we get from 1 multiplying to 1.5 and then multiplying to get to 2. Pretty sure it's going to be totally different, right? The geometric mean and average are just different, almost for every number ever. There are cases when they are the same, like the average of 3 and 3 and the geometric mean of 3 and 3 is still 3 either way. But let's look at this, okay? So what did I multiply to get from there to there? Well, I multiplied by 3 halves, right? I divided by 2 multiplied by 3. And then what did I multiply to get from 1.5 to 2? Shoot. Well, I divided by the 1.5 and I multiplied by 2. So multiplying by 2 and 12, I multiplied by 4/3. So those are not the same thing that you multiply by. So no, that is not always true. Okay, so not always. Then could we think of a time when they are the same? Well, we did think of a time. If they're the same number, they're the same, right? Oh, wait. Geometric mean for consecutive positive integers. Oof, man. So is there a case of consecutive positive integers? So consecutive means one after another. So we know it's not always. So let's think about is there a case when we have like a, and then the very next thing is a plus 1, right? Is literally the next integer. Is there a case when the average of those is the same? So a plus 1 over 2. So that is the same as, and remember how you solve for the geometric mean, right? If we go like a is to x as x is to a plus 1, and we solve, we get x squared equals a times a plus 1. And then we go square root, so x equals square root of a times a plus 1. Right? So we go, okay, so is that ever equal to the square root of a times a plus 1? This is some crazy freaking algebra. So, I mean, the average is always going to be the 0.5. Is there ever positive numbers where you multiply by the same thing? I think this is never, but I really want to solve this crazy algebra here. This seems like a deep rabbit hole to go down to, but this is what? 2a plus 1 over 2 equals this crazy square root. So we square both sides and we get 2a plus 1 over 2 squared equals, and over here we get, this is a times a plus 1, or a squared plus a. So let's multiply it. Why not? Okay. So this is, I should have multiplied by 2 first. Let's do that. Let's do that. So we multiply by 2 first. So we have a 2 here. And then when we square, we get a 4 times this. And then this is gone. So we square this, we get 4a squared plus, and then 2a times 1 plus 2a, so that's 4a plus 1 equals, and then distributing, we get 4a squared plus 4a. What the heck? We subtract these and we get 1 equals 0. That is never true. So it is impossible. There's no value of a that ever makes this true. Whoa, cool. So we proved it's never true. So yeah, never true. There was probably a much more elegant way to do it. But again, algebra, you can just always fall back on it. Really cool. The simple idea is that the average between any two numbers, 3 and 4, is always going to be the middle 3.5 that you added the 0.5. And when you want to get there, you would say, well, what would I multiply by? And that way that multiplication grows or shrinks is going to be different. If I'm multiplying 3 to gain a 0.5, and then I'm multiplying a different larger number to gain a 0.5, I have to multiply by a different proportion to gain the same amount because you have a larger number. It's like 5% of 100 is 5, but 5% of 200 is not 5 anymore. It's 10. So I can't multiply by the same number to gain the same value when you have larger or smaller numbers. That's another way to think about it. Really cool problem. Okay, so let's do another one. Let's do 36, the geometric mean for two perfect squares. So perfect squares are like 9, 36, things like that, is a positive integer. Okay, so the geometric mean, if we take two numbers like this, we're saying, what do we multiply by? Well, here's another way to remember it, right? If we go all the way back up to almost the top, right here, is the geometric mean is equal to the square root of a times b. And so if both of these are perfect squares, that's equal to the square root of a times the square root of b. And so, yeah, it will always work out to be a whole number. Let's go all the way to the bottom and actually solve an example, though, just to show. So if it's 9/36, we go 9 is to x as x is to 36. X squared equals 9 times 36, square root, and we get x equals the square root of perfect square times perfect square, which is always square root of perfect square times square root of perfect square. So it'll always work out. No, it was 3. It'll always work out to be a whole positive number times a whole positive number. So yeah, that one is always true. Cool problem, okay? What about the geometric mean for two positive integers is another integer? Well, that's definitely not always true because positive integer, the geometric mean is 3. So it's not another integer. But is it possible? We just showed that the geometric mean between 9 and 36 was, what, 3 times 6, 18? So sometimes it's true, and sometimes it's not true. So that's sometimes. Just to double check, what was that? 9 times 2 to get to there, and then times 2. Yeah, so 18 is the geometric mean. So that was sometimes. Okay. The measure of the altitude of a triangle is the geometric mean between the measures of the segments of the side that intersects. Oh yeah, that's sometimes, right? That's one of our theorems today, but the key is the measure of the altitude of a triangle, right? And it's supposed to be of a right triangle is the geometric mean between the so that intersects, and that's only true if you're talking about the hypotenuse. So there's 3. So if you have, for example, a right triangle like this, and this is 3, 4, 5, and you're saying, I'm talking about this altitude, well, it cuts this side into the bottom side into segments of 0 and 4. And so you would say 3 is the geometric mean of 0 and 4. I don't think it is, right? Nothing can be a geometric mean between 0 because you're saying 0 is to 3 as 3 is to 4. 0 divided by anything is 0, so it's never going to be equal to some positive ratio. So again, it's only true if it's 1, a right triangle, and 2, it's the altitude that goes to the hypotenuse. So this is sometimes, right, if you happen to have a right triangle and the altitude is going to the hypotenuse, but it's definitely not always true. I mean, for any altitude in any triangle, no. So that's definitely a sometimes. Cool problems. Okay, this one, find the value of, and it's just saying use it twice. That's it. Okay, so we're given AD is 12. We're given BD is 4. So we know this is the geometric mean of those. So we go 4 is to, I don't know, let's call it X. So 4 is to X as X is to 12. So X squared is square root of 48. I'm probably going to use, is just 48. And then X is square root of 48. I'm probably going to use that value, but I'll simplify it too. So X equals the square root of 16 times the square root of 3, or X equals 4 root 3. Okay, so we got that. And I mean, I shouldn't have boxed that. That's not the end of our problem. Now we need to solve stuff inside, right? Well, we could always go, if that's square root of 48, we could use the Pythagorean theorem and say, well, then this side, CB, is equal to what? Well, you go 4 squared plus root 48 squared equals CB squared. And so you go, okay, that's 16 plus 48, so that's 50, that's 64 equals CB squared. Whoops, CB squared. So that means CB is 8. Okay, so we got this whole segment is 8. And now we could use the theorem to say leg is, oh wait, which are we looking for? The exact value of DE. Oh yes, so we need that. So what we could do then, well, I mean, let's say we don't use the theorem this time. Let's just look at this triangle. So we could use the theorem. The way we'd use the theorem is to say this leg is the geometric mean between this piece and whole piece. And then once we did that, we go, okay, so now we have some length. I don't know, let's just make up a number and say this is 3. And then we go, oh, well, if that's 3, that means this is 5. And then altitude is the geometric mean between 3 and 5. That's the idea. But let's use similar triangles, okay? So we have this big triangle. And I'm going to put some angle markers. Let's do this one's 2 and this one's 1. Root 48 and 4, 2 and 1, is similar to this triangle. Oh, and this is 8. And that's a root 48. And that's similar to this triangle, which is double angle and right angle. And that's 4. Now notice, we have a completely solved triangle is similar to, and as long as we have one side length, bing, bang, boom, we got all the side lengths. So let's just solve for it. Now, I'm going to actually fill in a few things here first. I'm going to go, okay, well then that means this is the double angle. That means this is the single. Which side are we looking for? We're looking for DE. So let's put an X right here for DE. And now let's just do a proportion. So hypotenuse is to that side. So 4 is to X as, so hypotenuse of this triangle is 8, is to, and the X is the side between right angle and 1. So right angle and 1 is this one, root 48. And so we get 8x equals 4 root 48. Dividing by 4, or dividing by 8, we get x equals 4 root 48. I don't know why I did the root 48. Let's swap out the root. Well, we'll do that in a second. Divided by 8. We know root 48 is 4 root 3. So that's the same as 4 times 4 root 3 over 8. And then we go this and this cancel to be a 2 and a 1. This and this cancel to be a 2 and a 1. And so now we're left with x equals 2 root 3. Bam! Woo! What a cool problem. Hope you enjoyed the video, you guys.